Hello and welcome to the Electricity Northwest Respond webinar. Throughout the call, all participants will be in a listen-only mode and you can type your questions into the Q&A box on the web. Please also remember to give us your feedback in the survey at the end of the webinar. Just to remind you, this call is being recorded. I will now hand you over to Ben Ingham. Please begin your meeting.
Good morning everyone and welcome to our final webinar on the Respond project. I'm Ben Ingham and I'm the Respond Project Manager. I'd like to thank you all for attending today. Hopefully this webinar has something that will keep all of you interested. In terms of the agenda, we've got a bit of an introduction, a quick overview of the project, and then the intention is to run through the 3 techniques that were trialled, finishing up with a summary and next steps arrangement. The format of this webinar includes a presentation of roughly half an hour followed by a question and answer session. If I could ask you to submit your questions via the on-screen box during the presentation, and then we will come back to them at the end and answer as many as we can. So with me today on the panel is Paul Turner, the Innovation Manager, Steve Stott, who was the Technical Lead on the project, Kieran Bailey, who led the Trials and Analysis section, and Tracy Kennelly, who was in charge of the Customer section. So Respond is the first demonstration of active fault level management in the UK in an attempt to avoid traditional reinforcements. It's a £5.5 million project which was won competitively through the low carbon funding from Ofgem. The project started back in January 2015 and is supported by several partners who you can see on the screen there. And they were chosen to help maximise the benefits from the learning generated from the project. The trial phase of the project went live in May 2016. We've now come to the end, so we're in the closedown phase. A quick overview of what Respond was looking at then. So we were looking at ways, faster and cheaper methods of securing the network for fault level issues over and above traditional reinforcement. One of the outcomes we were looking to deliver was a buy order of solutions based on a cost-benefit analysis for various scenarios. We were looking to facilitate the active management of fault code in real time using retrofit technologies to supplement our existing plant, and additionally to come up with commercial arrangements. We were trying to look at enabling a market for the provision of a fault current limiting service using generators and other plant connectors to our equipment. We were looking to use our existing assets, as I say, with retrofit technologies applied to them, and also to ensure that there was no detriment to the health of those assets. And finally, we were looking to reduce customer bills by using this technique to defer reinforcement and the costs associated with it. So, real-time mitigation. For those of you that aren't 100% clear, for fault level, as it approaches the rating of switchgear and other items of plant on our network, we were looking to have a software-based system that analysed in real time and decided once a threshold had been crossed to enable the relevant technique. So there's 3 techniques trialled on the project: adaptive protection, the fault current limiting service, and the IS limiter, all of which were act to reduce fault level as a fault occurs. So the fault level assessment tool, or FLAP for short, this was a software based in our top-end SCADA system, which is currently being implemented. The idea behind this was it was performing real-time calculation of the fault level as the network changed, so that all combinations of circuits and load could be accounted for. It was designed to automatically control the on-site devices enabling and disabling as required throughout the day. Both of those we've managed to prove successfully in terms of the software was generating outputs in a timely fashion, and it was able to control the devices based on the outputs of those. The issue we had with this was due to the fact that we are transitioning from an existing SCADA system to a new NMS platform. Some of the data we had wasn't quite the sufficient quality to allow the results to be as accurate as needed for this project. So although we've shown that the solution is technically viable, there is some work to do on our data as it gets transferred into this new system to ensure that the outputs are usable going forwards. So the first technique we're going to go through is the adaptive protection. So already on our system we have devices which are designed to break fault currents, circuit breakers and fuses and various other bits and pieces at strategic points. The idea behind adaptive protection is effectively to change the order in which the devices operate in order to reduce the fault level and control the amount of fault current interrupted by each device to ensure that it remains within the rating. Using the redundancy built into our network at the primary switchboard and above to ensure that this can be done without any impact on our customers. What you can see here is an example of the setup used during the adaptive protection. So at the top of the screen you can see the two primary transformers which feed onto the primary switchboard. On one side of that we've got a sort of domestic and commercial mixed load, and the other side is more of a industrial type load. The red line in the symbol indicating that there's a fault occurring. So what adaptive protection does here is it looks at operating either the breaker feed controlling one of the two primary transformers or the bus section, which is the ones indicated in yellow. That allows us to reduce the fault level seen by the feeder circuit breaker indicated in red before it operates to interrupt the faulty circuit. So the idea is that we can resequence it and do this within a safe fault protection operation time, so we don't increase the risk of damage to our equipment. So what we've got here is the waveforms generated during the operation of one of our adaptive protection relays. We had 8 successful operations in total throughout the project. None of them were maloperations. They're all genuine faults that we would expect the system to work for. And one of the interesting things we saw was that the faults actually develop through their life cycle, as it were. So you can see on this one that the fault started just before the trace, unfortunately. So you can see we've got a phase to earth fault with the sort of the green line and the brown line, the grey line at the bottom representing the phase and the earth respectively. After a period into the fault, you can see that it develops into phase to earth as we believe phase then starts to increase the load. At this point, the earth current is reducing, but is still present. Once it becomes phase to phase in nature, the adaptive protection then detects this and looks to operate within 35.5 milliseconds. This triggers the circuit breaker controlled by the adaptive protection, which trips in just over 100 milliseconds to reduce the fault level. So you can probably just see there that the fault level does reduce. You can see that there's a reduction in fault level which should bring it within the rating of the existing breaker. There's then a further development as the fault progresses. It now becomes a 3-phase fault. Red phase picks up as well, but that's just before the feeder circuit breaker itself opens in 800 milliseconds, interrupting the fault and clearing it from the system. So that's a fairly typical example of what we saw during the operations we saw in the trials. Okay, so the next technique we have is the IS limiter. This is a physical device installed on the network which was used to either replace the bus section or the circuit breaker for one of the primary transformers at the site. The IS limiter is designed to operate in around 5 milliseconds, which is before the fault current has time to reach its peak level, which is much quicker than our standard protection equipment. When enabled, the IS limiter monitors the current flowing through the system, and when it detects a rise of current above a certain rate, it triggers a relay which detonates a small explosive charge akin to a car airbag. This causes a break in the bus bars, diverting the current through a fast-acting fuse. Once the fuse blows, triggering a circuit breaker to make sure that all three phases are disconnected. And as I say, it's designed to do that incredibly quickly, much quicker than we can manage with a standard protection circuit breaker arrangement. So we trialled the physical installation of the IS limiter at 2 sites during the project. The first was at a site in the Preston area, which is Bamber Bridge. So in this case, we use it to replace the bus section. You can see here, we're running the site with the bus section open and the coupling between the two sides of the primary switchboard through the IS limiter itself. So the idea here is that for a fault on any of the outgoing circuits, the IS limiter itself would open, splitting the board in two and reducing the fault level current observed accordingly. The second installation method we trialled was at a site in Manchester, Broadheath. In this case, we actually put the IS limiter in line with one of the breakers controlling the primary transformer. Again, the idea behind this was that should a fault occur on the network, the IS limiter would detect this, operate to remove that source of in-feed from the network and reduce the fault level to a safe level. Again, both of these you'll notice have a bypass arrangement such that if there's ever a need for system outages for maintenance or other needs, we could continue to offer the customers the level of security that they need. So we weren't increasing risk them at any point during the trials. So this next slide does a run through of a fault seen by one of the IS limiters. This is the one at Bamber Bridge, and it was recorded in May 2017. So we had a fault out on the network, which was seen by the IS limiter, a red phase in particular. This operated correctly to interrupt the fault. The time interval between the IS limiter reporting as operated to our top-end SCADA system and the opening of the control and breaker was recorded as 10 milliseconds. So as I say, that's much quicker than installed. The series circuit breaker opened 51 milliseconds after the tripping of the IS limiter. So the event log indicated that the 11 kV protection relay operated just over 1.3 seconds after the IS limiter breaker opened. Now this is probably delayed somewhat by the reduction in fault level. Now obviously, as this was a trial, none of the sites we tried this at had actual fault level issues. So as the fault level was reduced, it affected the time it took the standard protection to operate it in. One thing to note on this is the speed of the operation for the IS limiter is such that the fault recorders installed in the project were not fast enough to capture the waveforms as we could for these active protection, which made it much more difficult to analyse the operation. But we have enough information to say that the technology works. So here you can see the operating IS limiter. So you can see the closest to there to you on the left-hand picture is the red phase with which is operated. The sort of the brown protrusion at the top is the striker pin, which has then triggered operation of the series circuit breaker, which has ensured that all three phases have been disconnected. On the right-hand side, we can see the green operated pin has popped out. That's to show that the explosive charge has functioned correctly. So this insert can then be returned to ABB for refurbishment and then be returned as reused. So it's not to sort of use it once and that's it arrangement. And again, this is a couple of pictures from the second operation where the yellow phase is operated on this one. So you can see it's the central one. Again, we've got the brown striker pin protruding and the green button has been pushed out to show the charge is detonated. As well as the physical installations, we also installed a number of sites where we just had the sensing sites, effectively the relays. We had one successful operation there which showed that on that site as well, the IS limiter had the physical technology being present would have operated. So we have two operations of the physical device plus one of the relay alone to show that the technique was viable. Okay, so the third and sort of final technique we looked to trial on the network was called fault current services. This was designed to be an arrangement we had in place with various industries across our network which had large rotating plants, generation and such things that could contribute to fault level on our system. It was a commercial solution designed to reward customers for providing us the facility to interrupt parts of their equipment during faults to reduce the fault current seen by our equipment and reduce it to safe levels. The challenge really was to identify customers who were willing to take place in a trial of this service. So before we go into the details of it, so this is a quick diagram demonstrating the setup of the system. So you can see here again we've got the primary switchboard at the top of the diagram. On the right hand side we've got our standard customer load with domestic, commercial, what have you. And on the left hand side we've got some industrial load, a wind farm, and then we've got a customer who's kindly allowed us access to the control and breaks of their CHP plant as part of this service. Again, the red arrow is indicating the location of the faults on our system. Similar to adaptive protection, the technique here resequences the operation so that the yellow breakers down on the bottom left interrupts from the rotating plant and generation included on the customer's network. That reduces their contribution to fault level on our system below the threshold for safe operation of our equipment, allowing us to then trip the feeder circuit breaker on the right hand side, removing the fault from the system. So as part of the approach to this in terms of trying to find people who'd be interested in assisting us with this trial, there was a survey carried out in conjunction with Energy and ADE, who are industry bodies for CHP and other generator type equipment. They helped us to identify a number of customers who had suitable equipment for trialling this sort of technique. In terms of working with them, we identified that the ideal target market would potentially non-manufacturing industries and those able to constrain their generation for periods of up to 10 minutes without significant impacts on their business. So, as I say, we sent out 750 surveys, of which we got a massive 103 replies. Of that 103, 47 people were in our region, were suitable industries and generation types, and had actually expressed an interest. Following further discussions with them, there were 30 people who were willing to engage in a detailed discussion of our requirements, leading to a whole 0 contracts being awarded as part of the project. Now, this was for a number of reasons. So a lot of people, when we discussed it with them, expressed concern over the risk to their processes by losing generation in an uncontrolled manner with no prior warning. A lot of people felt that put them at risk for financial loss. There was also nervousness about the number and duration of constraints they would expect through the year. Unfortunately, with it being a fault response service, we can't control when we have faults and where, so we were unable to guarantee to limit it to a minimum number of operations per the year. There was further concern on the impact of their operation, especially in terms of exportability and also other contracts they had with the other parties, especially National Grid, in terms of the capacity market and the triad. They're also concerned about reputational damage from occurring from these losses. There was also a unease at releasing control of their equipment, so having somebody else suddenly be able to disconnect parts of their plant without reference to them didn't sit quite right with some of them. Especially ones where it would mean additional costs in terms of potentially having staff on standby to deal with the consequences of that shutdown. Financial incentive did appear to be a key driver for this market, but only if it was sufficient in their minds to cover the risks and loss of revenue, which especially in terms of the triad markets can be quite significant for some of these customers. It wasn't something we could really compete with in terms of the projects. So lessons learned from this. So the transition from expressing an interest to a service through to actually being able to participate in it requires a need for greater awareness, both on our part in terms of the drivers experienced by these large commercial industrial sites, but also perhaps from them in terms of what it is we're trying to achieve. It was a good learning point for us as well was the actual impact that a loss of critical plant, even for 10-minute duration, can have in terms of knock-on effects for these businesses. Which means the assessment of the way that the risk versus the incentives and savings available is fundamental really in the organisation's decision making when they decide whether they want to enter in this sort of agreement with us. As mentioned previously, one of the main conflicts we had was with their provision of other services. So where they're already committed to provide services for National Grid, there is a reluctance to engage with us in terms of fault monitoring service because it put their participation in these other markets at risk due to the uncontrolled nature of when faults would occur. However, based on the learning from this, there is still the potential to develop this as a market, particularly in terms of new connections, where we could offer it as an option when joining the connection agreement as to whether they would consider going down this for some saving or financial incentive. This is probably a better fit than trying to retrofit this agreement into an existing customer, especially in terms of installing the equipment needed at their site. So, quick summary of the project then. So we've demonstrated that the fault level assessment tool can be used to calculate near real-time fault levels and successfully enable and disable techniques as required in order to minimise the additional risk in switching. Both the adaptive protection and the iris limiter were installed, trialled and have been demonstrated to reduce fault level over multiple events. The fault limiting service, while we've demonstrated technically it's feasible, there's still work to be done in order to generate some sufficient commercial appetite for the service. Safety cases for each of the techniques have been produced, peer-reviewed by another UK DNO and are published on our website by the end of this month to show possible further constraints in terms of using this from a safety point of view. Closedown report is due for the end of October. There'll also be a presentation on this project at the LTNI project, which is mid-October, if anyone really wants to attend. And going forward, we're now looking at taking the learning from this and the updates to our policy and procedures generated and integrating that into our business as usual procedures in order to allow the potential to use these techniques in lieu of traditional reinforcement methods where suitable going forward. Thank you all for your attention today. I hope that was informative. If anyone has any questions, or we'll have a look at what's been submitted and we'll start working our way through them now. So as I say, you can submit any questions through the on-screen box, and then we'll work our way through as many as we can. Thank you.
Okay, so the first question then is, which of the technical solutions do you think works the best?
I think in terms of the projects, that's an interesting one. So it's difficult to say that one technique was superior to the other. So between adaptive protection and the iris limiters, which were the ones which we trialled in anger, as it were, they've both shown to reduce fault levels successfully, and it's more of a site-by-site analysis as to which is more suitable. Obviously the iris limiter clears much faster, so if you have issues, not just with the switchgear, but potentially with cable runs and things like that, that would potentially be a better fit. Whereas the adaptive protection, being more of a retrofit solution using the existing relays, provides more of a potential cost saving. So it's a case of balancing the needs and benefits of both solutions on a site-by-site basis, really.
Do you think that the fault current limiting service is viable post-trial?
I think this is one for me, Paul. Yeah, I think this question probably popped up before Ben had a chance to complete his synopsis of the SCL service. In terms of an elective service for existing customers, we have not been able to engage with customers like a huge engagement piece of our part, which seems to demonstrate that at this particular juncture there is no commercial appetite for this type of commercial service in the marketplace, and that is largely driven by customers that would potentially be suitable to provide this tend to already have existing commercial arrangements with DSO that are quite lucrative, and they are extremely understandably loath to jeopardise those in any way. Moving forward into the DSO world, and those constraints and those synergies start to get moved out, potentially, where this actually sits far better, as Ben has explained, is as part of a toolkit for a range of managed and constrained connection agreements. There are issues concerning having what is effectively adaptive protection in customers' own premises, and we would have to look at the safety case on an individual basis to assess whether or not it is actually viable from that perspective going forward.
Thanks, Tracy. What financial incentives were offered on the fault current limiting scheme?
Yeah, we based this calculation on the previous DSO type arrangements. It was very, very loose, and part of the survey was trying to establish a suitable price point. We went in at, based on that and based on a 10-minute constraint, we based an indicative price point of about £2,000 per MVA, just as a starting point. And we tested whether or not customers would be prepared to enter into availability or utilisation payments. That understandably seemed to be an undervaluation, and customers weren't prepared to engage at that particular level. We didn't expect that to be the case. And what we did in the survey was to actually open it up to try and establish that price point, to establish what customers would need. The difficulty that we had, those customers that were prepared to engage, the risks of loss associated with just a 10-minute constraint for those customers, driver in terms of the commercial the financial benefits that they would be seeking to recover. And unfortunately, because they weren't able to directly engage and understand that cost benefit, it's not been possible to establish a price point.
Can you confirm the voltage levels at which solutions were demonstrated? How well you think the solutions were transferred to higher and lower voltage levels?
Yeah, I think the voltage levels that we chose were all either 11 kV or 6.6 kV for these trials. There was some 33 kV work done as well. I would suggest that they could be used at different voltages, possibly 33 kV for an IS limiter. I don't think there's something that you'd want to start transferring down to LV. It'd be difficult to construct, difficult to implement. Adaptive protection is certainly something that works well at 11 kV with a lower level of unit protection. So I think it's something that's really best suited for the most part to 11 6.6 kV.
How often would the fault current limiting be expected to be used?
Again, as Ben has said in his presentation, that was one of the sticking points in actually getting customers engaged, because it's very difficult to know that at this juncture. Again, it was one of the concerns that we had. But the service would only be activated when flat 2 was enabled and fault level on the network was high and there was a fault on the network. We based an assumption of 2 events per year, but again, that was just indicative. If the fault level SEO service were to be taken forward as a BAU solution, as a managed connection, there would be no actual payment to be paid to customers, but any customer that was offered that type of arrangement, we would go back and do a search on the fault level history, probably for the last 5 years, to give the customer some indication of an indicative level of constraints.
How stable is the actual fault level on your network?
Yeah, I'll say that. It's from the data that we retrieve from the network studies, from the devices installed, we can say that relatively is stable. From a real-time fault calculation, this will remain stable, but the changes are based on network activity. So any reconfiguration of our own network and any changes on National Grid's network will cause basically a network impedance change, reducing or increasing fault level. However, the other big aspect of this is generation. Now, most SCADA systems, DNOs don't always have visibility of generation, so there is an unknown element of real fault level from simulation type studies that all DNOs carry out. But on the whole, we'd like to think that we're in a stable situation with fault level.
Which organisations did you approach to take part in the fault current limiting service trial?
Okay, well, the aspiration was to take forward 5 FCL service contracts as part of the trial, with a real aspiration to have 2 one demand and 1 generation contracts. So to do that, we thought we partnered with the ADE and Energy, who have got probably a closer relationship to customers than we have, to try and engage to help bolster those numbers. Obviously, because we were unable to secure a contract that demonstrates that wasn't really successful as we'd hoped. In terms of the customers that we approached directly, we identified about 1,600 industrial and commercial customers, and from those there were all our HV connected customers. We used our DG database, we looked at all customers where we have got private arrangement, construction and management agreements. We looked at connection applications that were going through. So we really trawled every conceivable customer type to try and engage. And as Ben said, there was an aspiration to survey 750 customers, and from those we hoped that there would be a sufficient pot to try and engage these 5 customers to take part in the trial. And despite, again, repeated engagements, there was a huge amount of concern from customers that actually were willing to engage and were able to take the trial forward aggressively.
It's probably worth mentioning as well that we did prove the technology, so we have proved and trialled the technology in terms of providing service, specifically if it is required for new connection customers. Is the fault current limited service only initiated under fault conditions? How do you ensure this action is taken prior to conventional protection actions and within safe timescales?
Yeah, so if we would have managed to get the fault current limiting service to have been used directly by a customer, as opposed to just proving the technology, the idea is that you have an instantaneous setting on the device at the customer's premises, which is providing the extra fault current. So you really have to have conventional protection upstream, which will clear in a sort of reasonable time period of up to say 1 second. Because essentially what you're doing is reducing the fault current contribution. It's not for clearing the actual fault. So it has to be pretty much instantaneous, and you have to be guaranteed that that setting is the setting that will be used going forwards, i.e. the customer can't just change that setting. That's something that has to stay that way for the future.
This is one of the security concerns about actually having this type of commercial solution at the customer premises. And again, there are safety issues that would have to be ironed out before this type of solution was taken forward. Just incidentally, it's worth noting that once we have actually had an operation of the FCL service at the customer's premises, it will be up to the customer, because of safety issues, to actually reclose the breaker themselves. And that again was one of the issues that we had in taking this forward, because whilst we only required the constraint for 10 minutes, the reality of that is that customers are unlikely to have that kind of resource on site. So what is a 10-minute constraint for us could be several hours, if not longer, for an actual customer.
Yeah, I mean, there is an option for us to automatically close up, but a number of customers didn't want that to happen. Do you have any outstanding safety issues with the equipment used?
In terms of the trials that we carried out, obviously none of the sites had a fault level issue, so even if the equipment had fails, we would have been able to safely instruct any faults that occurred. As I said in the presentation, we've had safety cases generated for all 3 techniques based on learning from this and the proposed, in the case of the fault limited service, the proposed solution, which have looked at the risk and advised, from a safety point of view, any considerations to be taken about where they're used. So what we saw during the trial was that both techniques operated consistently and operated as expected. It's worth noting as well that although the IS limiter has not been used by DNOs in this country so far, it has been used in various other countries and amongst industry for some time, so it is fairly well proven technology.
It's worth saying as well that adaptive protection essentially is using the same technology that DNOs and many industrial plants all over the world use to protect their networks, so it's not doing something that's unusual in that regard. It's the same level of kind of reliability that you'd expect from normal protection on a public system.
We investigated common mode failures, and we've looked at various options to take them out of the system as well. So all we can say is really, during the trial we had no failures, everything worked correctly.
Right, I think that appears to be the questions, so thank you all again for your time today. As I say, we will be presenting on Respond at the LTI conference in Telford in 3 weeks, so if you want to come along to that, or if you want to come and see the team and you think of any questions afterwards, you can do that, or you can email us. And if I could ask all of you to please complete the post-webinar poll that will be popping up on your screen shortly. That would be much appreciated. Thank you.
Thank you. This now concludes our session. Thank you all for attending.